All right, everyone, welcome to chapter 23, lecture 2. In this video, we'll be talking about some reactions that amines do that don't have super strong analogies in carbon chemistry. So previous lecture, we learned a lot of things about nitrogen that were largely analogous and largely similar to carbons. Today, we're going to be talking about some nitrosonium chemistry. And nitrosonium is a specific cation, NO+, that has very interesting and important reactivity, particularly with regard to the synthesis of organic compounds through the 1950s before more modern methods were developed. So this is an important class of compound. We're going to want to learn how to use it and understand how it reacts and what the arrow pushing mechanisms are for its generation. So today, by the end of class today, you should be able to draw a mechanism for activation of sodium nitrite, which is this compound here, circled in green, sodium nitrite to form nitrosyl cation, also sometimes called nitrosonium cation. Predict the product of reactions of various classes of amines with nitrosyl cation and draw a mechanism for these reactions. Draw a mechanism for the reaction of aryl diazonium salts with water. We'll talk about what an aryl diazonium salt is. Predict the product of reactions with aryl diazonium salts with various reagents. Draw a mechanism, predict the product, including selectivity for the Hofmann elimination of quaternary ammonium salts. This is where we go away from the nitrosonium and start talking about N+ leaving groups. And finally, draw a mechanism, predict the product for the cope elimination. This is something we'll talk a little bit more in class, so we might not get to that in this video. All right, so the formation of the nitrosyl cation is almost always done under acidic conditions. And the way this reaction works is we take sodium nitrite, which is stable. It's actually a food preservative. We protonate it to give HONO. And HONO is sort of like a nitrogen derivative of formate, compound we might have learned before. And this can actually undergo further protonation. It takes a relatively strong acid to do so. And we protonate at the OH oxygen. And you may be saying all this stuff, hey, what about resonance and all that? Indeed, the other oxygen at the top is more basic, but it doesn't lead us to product. Remember, these things are in equilibrium, and sometimes an uphill step is required to get to product. So that gets us to the protonated nitrosyl compound, this one shown here. And then we've made a really good water leaving group that generates NO+. And this NO+ breaks a lot of the rules that we've learned so far. And that we don't want to put a cation on an electronegative atom. Nitrogen is. Not only that, nitrogen is attached to an electronegative oxygen atom. But in this case, the protonation driving force sort of overrides that where we generate water. But these things are in equilibrium. So you don't, it's true that nitrosonium cation is not the primary product that the water can reattack and go backwards. But this is how we generally consider the generation of nitrosonium cation. There are other ways. And this nitrosonium cation can react with nucleophiles. It is indeed quite electrophilic. So it could react with the nitrosonium, could react with tertiary amines. However, this reaction doesn't work super well and it actually goes backwards. And since these are an acid, what ends up happening is the nitrogen gets protonated. However, with tertiary aromatic amines, we can actually, and we'll talk a little bit more about this in chapter 20, have the group attack and then we lose H+. And again, this is done under acidic conditions as well, but we need this lone pair here to donate all the way through the aromatic ring to form the nitrosylated product here. And this only happens with tertiary amines, and it generally happens at the 4 position. Nitrosyl compounds, which are this class here, can also be a nitrosamine, as we'll talk on the next slide. These are actually quite toxic, and they're a common impurity in food that leads to cancer. And so secondary amines, whether it be aromatic, something like this, an amine with an arine off of it, and a phenyl group, or secondary regular aliphatic amine, aliphatic again meaning just saturated hydrocarbons, these can react with the nitrosonium cation, which is electrophilic at nitrogen, to generate after the loss of H plus to generate what are called nitrosamines. And nitrosamines are also impurities in food that happen when you overcook them sometimes, and they are also quite toxic. They, as far as I know, they don't really have a huge number of synthetic purposes. Because they're so toxic, they generally don't find their way into pharmaceutical drugs. But again, this is just nitrogen's lone pairs acting as a nucleophile and the nitrosonium cation acting as an electrophile. And what happens is you get to an intermediate like this. And this ammonium here is a lot more acidic than normal and a weak base in solution. Generally, you do these things in water. Can come along and deprotonate it. And this is a reasonable thing. You can think about the effect that having a nitrogen double bonded to an oxygen would have on the stability of an ammonium cation. And it's certainly going to make it much more acidic because it's very electron withdrawing, both resonance and inductively. So moving on to more interesting reactivity, if we protonate primary, or if we nitrosylate primary amines, we actually get a relatively different reaction outcome. And the reason for that is because we can get to an intermediate that looks like this, where in this case, if we had methylamine, we could get to the N-nitrosomethylamine. And what ends up happening is that through a series of protonation steps, and we'll talk about this in a slide or two, we actually get to a dinitrogen leaving group. And nitrogen is the world's best leaving group. I made this trophy here for it because it's so good. It lets us break the rules. Okay? And one of the rules we learned in organic chemistry the first semester is that we're not allowed to make primary carbocations. Well, dinitrogen is such a good leaving group. It's so happy to leave. It just says, see you later, I'm out. That it will let us generate a primary carbocation. So this is pretty much the only time in the class where you can generate a primary carbocation. And this, what this does is it's pretty problematic because primary carbocations are very reactive. And so they'll just like self-immolate. They'll turn into a million different products. And it's just not very useful. There are some exceptions to that, and it can be used to useful effect in intramolecular fashions, okay, to do controlled chemistry. We say intramolecular, that's a molecule reacting with itself. And so here's an example of a controlled use of a primary carbocation, what's called the Tefino-Demyanov reaction. And in this, we generate a primary carbocation. I should finish this. This leads up here. We generate a primary carbocation through this nitrosonium H+ sequence. It also generates an equivalent of water. And if we generate one in a strained ring like this, we can actually have an alkyl shift to generate a 5-membered carbocation, and this can be carried forward to a variety of reactions of carbocations that you might have learned about. For example, elimination would be one such possibility. And so just please note, this is almost the only time it's okay to make a primary carbocation. We're breaking the rules because nitrogen is just really that good of a leaving group. It will leave behind a primary carbocation. The exact nature of that, if it's a true free-floating carbocation, is a subject of debate. However, it generates what is effectively a primary carbocation. And so this leads us to one of the most useful reactions of the nitrosonium cation, or nitrosyl cation, you might hear both, is that reaction is with primary aromatic amines. They react to what's called an aryl diazonium. And this is ancient chemistry, at least by organic chemistry standards. This dates back to the 1800s, before people barely even knew what atoms were. And they found that this aryl diazonium compound could react in a variety of ways. And you can imagine why this would be very useful. An aryl diazonium can react with water if you heat it up to generate a phenol, an aromatic alcohol. An aryl fluoride, incredibly important in pharmaceutical development. Chlorides, bromides, cyanides, iodides, and just reduction to the H. These are all incredibly important reactions. And so you can imagine that if you're trying to make a molecule and you can make an aryl diazonium, you've got a lot of options to generate new molecules. And that's oftentimes what people want to do. So the way that this reaction works is a lot of proton steps. So the first thing we do is we generate our nitrosonium plus through a mechanism like what's shown. I guess I didn't show it. So I'll draw it out here. We'll generate our NO plus using acid along the bottom here. I'll show you how to make that. This generates the HONO. So I covered this for the most part on slide 2, but just to review, we protonate again, and now this is one of those rare instances where resonance leads us astray, so take note. But we protonate at the lower oxygen to make a water leaving group. And this gets us to our NO cation. Okay, and again, electrophilic at nitrogen. All right, so if we take our NO, we get to AR, just means aromatic, so something like phenyl. Something like this, a cation like this. And in these diazonium formation mechanisms, we'll usually use water as our base because these are usually run in aqueous strong acid, like aqueous hydrochloric acid. And we do a little proton shuffle here. The pKa, again, of ammoniums with an NO off them is much, much, much lower. They're much more acidic than a normal nitrogen. That's because the NO is inductively and resonance withdrawing. And what we start to do here, and again, I don't think in these sort of complicated reactions here, we don't want to memorize individual arrows. This first step, we add the NO plus. Sorry, there should be a plus there. The second step, what we're trying to do is trying to generate a water leaving group, okay? That's what we're doing from here all the way through to the end. Because water is a good leaving group, and that's ultimately where we want to go. You can see that we have an N2 up here. That means we're going to generate a nitrogen-nitrogen bond. We already did that in the first step, so now we got to get rid of that oxygen. A little logic here goes a long way. I'm not saying it's easy to do, but I'm just saying it's much easier to learn why we're doing something than it is to memorize exactly than it is to memorize exact arrows and not have any sense for why you're doing it. So I'm going to draw this compound in this resonance structure here. If you don't know how we got here, let's see, we can draw these arrows coming up. This is almost like a nitrogen enol, and we're going to deprotonate again. This is, once again, in an effort to make a water leaving group. So we just have to shift our protons using our water bases. And this is going to let us, we're basically just adjusting to get to that water leaving group. Get to something that looks like this. And we're actually going to protonate our water, our OH, one more time. Again, this is to form that water leaving group. And you can see that our bond order on nitrogen keeps increasing. I purposefully left that out because I want to show you the resonance structure in the context of our product. So an aryl diazonium has a structure, a Lewis structure that looks something like this, where you have an N3. And this explains why it's so reactive, is that dinitrogen looks like this. And you can see a strong analogy of N2 here. And N2 is the world's best leaving group. So this great leaving group off of an aromatic helps prime it to do all sorts of wonderful, interesting reactivity, like what we see here. And so from here to here, all we're doing is generating a water leaving group. And you just need to do that by successively pulling off protons from nitrogen, using water as a base and then reprotonating the oxygen. So the way that works is pull H plus. And that is the mechanism of diazotization. All right. So you need to know this mechanism. It's a common organic chemistry 2 mechanism that describes a very important class of compounds. And so these diazonium salts react with a variety of reagents, including water, to make useful compounds. So this reaction goes through something like this. And N2 is such a good leaving group that it can generate a carbocation on phenyl. And this is really bad for a variety of reasons. Foremost is that this is a sp2 orbital. If you can't convince yourself of that, you need to pause the video and draw it out. And sp2 is an orbital that stabilizes anions, not one that stabilizes cations. So there's a pretty important concept here, and that's that sp2 and sp orbitals destabilize cations. sp stabilizes anions. sp2 stabilizes anions relative to sp3. More S character means that the orbital is closer to the carbon. Closer to the carbon means it's more plus, the nucleus, I should say. So closer to the nucleus is more plus. The nucleus is full of plus charge. And so cations are less happy if they have more S character. And then water attacks this. Because this is a very unhappy cation. And so another reaction that can occur is through this diazonium in between, and it can generate fluorobenzene. Now, fluoroarenes are incredibly important in pharmaceutical development. Fluorine is not an atom that's found in your body. It's a very abnormal thing, and so our body can't really process fluorine atoms. It doesn't know how to metabolize them very well. It doesn't have the tools to metabolize them. So fluorinated compounds are really important if you want a drug to not be metabolized. And so people are very interested in making fluorinated compounds. And so this Balch-Scheinman reaction is one such example, where you heat up your arene and you get your carbocation, and it actually does something pretty weird here. It strips a fluorine off of the tetrafluoroborate. Whoa, my goodness, I drew those arrows backwards. So again, this is changing a fluorine sigma bond to boron to a carbon sigma bond to fluorine. Some other reactions of diazoniums are with copper metals. Copper chloride, we'll put a chlorine there. Copper bromide, we'll put a bromine there. And copper cyanide, we'll put a cyanide there. And these are all important synthetic transformations, and they require the corresponding copper salt. You need to know that these copper salts can generate the corresponding halides here and cyanides. If you react a diazonium with iodide, it doesn't need the copper. Iodide is the one exception to this. You do not need to know these mechanisms, but you need to know reactions. Okay. These mechanisms are a little bit advanced for this class, so we won't be talking about them. All right, so we're going to switch gears here a little bit. We've been talking about the chemistry of nitrocyle cation. Now we're going to switch and talk about ammoniums. All right, and so ammonium ions, NR4, something like this, will end up eliminating, remember elimination reaction from orgo-1 to generate the amine in water. And so ammoniums are not terrible leaving groups. They're not the best leaving group, but they're also not terrible. And the way this reaction works is we have a proton hanging out here that we don't really see. And what this can do is actually, I'll draw it down here, make it a little bit more clear. We'll talk about this on the next slide as well. Remember from organic 1, if we have a strong base and a good leaving group, we can do an E2 elimination. And when it's with an ammonium leaving group, it's called a Hofmann elimination. And the side products of this are the amine, and in this case, water, because hydroxide was our base and it's now been protonated, so these are the products. The Hofmann elimination is not really done in that many instances, but it does work. And so, again, this is just a review from organic 1 that if we have something like this over here, draw out that molecule, what it looks like, there's 2 products that we can have if we have something like sodium methoxide. We can have the secondary amine. We can have the secondary alkene. We can have the primary one. We can actually have 2 different geometries of these. So we can get 3 products. 75% of them are going to be the cis and trans butene in this case, because it's Zaitsev's rule, more stable. So an interesting part of the Hofmann elimination is that this reaction, let me highlight this here, this reaction forms way more of the primary alkene. Okay. And so the Hofmann elimination is unique in this respect. So if you need to make a primary alkene, you might work on the secondary amine. And so if you were in lab and you said, hey, I want 1 butene, not 2 butene, major product, you could actually make this happen by forming the ammonium and then forming the hydroxide counterion. All right, so the selectivity is different. So you need to know the reactivity. And then no selectivity. All right, so this preference for the thermodynamic, the more stable alkene, this is called the Zaitsev product. Or Zaitsev's rule, where that the more stable alkene is the more substituted one. And this is true for anionic LGs. Hofmann elimination products are the less stable alkene. Okay? So eliminations involving a neutral leaving group almost always follow Hofmann's rule. And so this is a neutral leaving group. Once it leaves, it becomes neutral. So this is a Hoffman product, or Hoffman rule. Okay, and then the bulkier the base, the greater percentage of the Hoffman product. So if we have, some hydroxide base, we'll get a good selectivity for the primary. But if we had something like terpbutoxide, much bulkier than hydroxide, we get more Hoffman. All right, so I'm going to end the video here. It went a little bit longer than I wanted to. We'll talk about the Cope elimination in class. The Cope elimination is sort of an intramolecular variant, or could be thought of as an intramolecular variant of the Hoffman elimination.